So let's start our evening session, and we have the first talk by Jan Pawlowski. Please, Jan.
Yeah, thanks for the introduction. And of course, it's a great pleasure being here. Actually, it's for some reason, my first time in Florence. I had some sightseeing, if you wish, yesterday, and some enjoyable food and booze. So it's great. And also it's great to have a real on-site conference again, at least partially. So I think you all agree on this. But I would like to give you an overview on the phase structure of QCD with functional methods. And I will guide you through some results of my group and also other groups. We joined together actually in a collaboration, which is the FQCD collaboration on functional methods, Dyson-Schwinger equations, and functional renormalization group. But I will also refer to the results of others. So where do we stand? Tatjana already has said it, and she said it already in Erice half a year ago, and now she repeated it. The future is bright. And I will not repeat what she said about the different facilities, because she's, as an experimentalist, far better suited to do this, and she did it very nicely. I would now point also at the theory perspective, and it's summarized in this cartoon of the phase diagram of QCD, where the main theoretical result you see here is on the chiral transition line of QCD, including potentially a critical endpoint. So what you see here are lattice results, functional RG results, and I would like to guide you through a bit how we obtained the functional renormalization group and also Dyson-Schwinger results here. So it was also mentioned there's a freeze-out curve. I mean, I put in the one we have obtained recently when we looked at fluctuation observables in QCD. And just to rehash, in my opinion, the most interesting region we have here is the region what I now call of new physics, might be a critical endpoint, might be something else. And so when I say critical endpoint from now on, it could be also something else, which is just new physics. Okay, that's the region. The color is a bit different than on my talk. It should be green. And we have various experiments here. Hades, CBN, star were already named, and Claudia also made a nice compilation of the other experiments you can also see here on this slide. Okay, functional approaches. This is a QCD approach. So we're not talking about models here, and the functional equations I'm referring to, I will use here, are summarized here. These are equations for the full free energy of QCD. And what you see here is a bunch of loops. And when I refer to loops, these are not perturbative loops. These are the full correlation functions of the theory. And one of the nice properties of these equations is they are closed. So you see here, so this is the free energy. So if you wish, the partition function of the theory, and the K here, or T, is a renormalization group scale. So I'm sliding, I'm the momentum scale, I look at the theory, and the free energy or partition function reacts on this change by having a bunch of one loop diagrams. It's one loop in the full correlation functions of the theory, but nevertheless, it's one loop closed. I have not dropped higher terms. This is a closed equation. The same is true for the Dyson-Schwinger equation, which maybe is better known. It's the quantum equations of motion. There again, I have the free energy of the theory. I make a variation with respect to one of the fields in the theory. Here it's the gluon. And the theory reacts to this by having a bunch of loop terms. And in QCD, this is a two-loop exact equation. Yet again, these diagrams here, I mean, the propagators we have here, so this gluon line, for example, here, or this gluon three-point function here, are the full correlation function of the theory, right? So it's closed, but it's a highly complicated equation. And of course, we cannot solve it exactly. And we have to resort to approximations and the systematic error controls, which goes with evaluating the predictive power of these evaluations. That's the biggest part of our work, if you wish. Okay, so just as a snapshot, that's actually a snapshot or a cartoon of the best truncation we are using at the moment for vacuum QCD. But apart from that, this is all interesting, I want to go directly to the equation which governs, this is a flow equation, which governs the two-point function of the quark. It's given by the scale derivative of the quark. So that tells us about something about the momentum dependence of the two-point function of the quark at a given momentum scale. And that is given by a bunch of one-loop diagrams. So now you see that all the different parts of the theory enter this. So we have the quark glue sector, which is black. We have the glue sector, which is yellow. And we have the quark meson sector, so the quark hadron sector, if you wish, which is blue. And already for this simple correlation function, but it's a very pivotal one because it tells us also about the chiral condensates, which we will use as the order parameter for confinement. All things go in. So you see the gluon lines, you see the quark line itself, and you see the quark gluon vertex, the quark meson vertex, and so on. Okay, so all the correlation functions you see and you have to compute go into the equations themselves. So all correlation functions turn up on the left-hand side of this equation, and they turn up in the loops. Okay, and of course, what we are aiming at is to improve our truncation. We're doing this constantly to, at the very end, have some where we can say, if you look, for example, at this quark correlation function, we see apparent convergence. Like in perturbation theory, you go to the next order and you see nothing is changing anymore. Okay, so let's look at this equation again. So on the left-hand side, you have either the scale derivative of this two-point correlation function, or you have the correlation function itself in a Dyson-Schwinger equation. And now we're interested in going to finite chemical potential. So this object here depends on chemical potential. The loop now depends on this correlation function itself, which depends on chemical potential. It depends, for example, on the, okay, so this should be the quark gluon vertex, so there should be a gluon in. I don't know where this disappeared. So it depends also, of course, on this quark gluon vertex, right, which also depends on chemical potential. Then there are further correlation functions, and at the very end, there is an explicit dependence on chemical potential. So that is the analytic structure of this equation. Now, if you solve this equation self-consistently, which means everything you see on the left-hand side is also put back on the right-hand side, this defines an analytic function. Okay, by solving this functional equation self-consistently, this defines you an analytic function, which means that if you have such a truncation to your full functional QCD computation, which passes all benchmark tests at lower densities, this defines you an analytic function in the whole complex plane, which has QCD information in it. So given, if you wish, hardcore and solid results for small density, this defines you a QCD extrapolation, if you wish, for higher densities. And it's the best you can get. You may question the reliability wheresoever, but this is the best you can do for higher densities, if you have agreement with whatever you know for lower densities. Right? It's an analytic function. It gives you every physics you have, I mean, in these approximations which do this, which means you have the best prediction for higher densities you can get. Okay, so that's what we are after. And at the very end, you have to judge whether we are coming close to it. That's, of course, up to you. But I think it's a great opportunity to get our hands on high density QCD, and essentially a combined approach. We have to use everything we have to get our hands on this. And then we can get our hands on this physics, localizing, if it's there, a critical endpoint or the onset of new physics, get our hand on transport, and I will now flash a bit results. I mean, it's 45 minutes, so there's not infinite much time. Okay, so that is where we stand, and I will now explain you a bit where we are in getting our hands on phase structure for larger density. Okay, so how do we define, for example, the transition line? It's the standard definition, and we have already seen in a way this plot or a similar one before. So we are looking at the chiral condensate. There are various chiral condensates, and we have computed quite some of them. This is the so-called renormalized chiral condensate, where you take the light flavor chiral condensate and you subtract the chiral condensate in the vacuum. You see it here. And that takes away the renormalization issues you have with the chiral condensate. You can also take the reduced condensate, which has such a subtraction in the light strange sector. I will show it later. In any case, you can compute this at 0 density. We did this, and you see it in comparison to lattice data, and we took the lattice data from the Wuppertal-Budapest collaboration, but of course, I mean, it's the same for the QCD collaboration. And this is not only done by us, but also there are nice results by the group of Christian Fischer and Gießen, and I refer to this here. Okay, and then you can go on and go to finite density, and you see how the chiral condensate changes. Okay, so at some point you go to densities or chemical potentials which are larger than the ones you have lattice results, and then this is a prediction or an estimate. I will also tell you about the difference in our wording there. Okay, so you can do the same, as I said, with a reduced condensate. You compare to lattice data, and for chemical potential 0, it's bang on. Okay, another benchmark test is the curvature of the phase transition line. So you can compute this. What I show here are results from the FQCD collaboration, and we have it both for Dyson-Schwinger equations, for functional renormalization group equations, and these results are in line with the respective lattice computations. Okay, so the results I will show now in QCD pass the benchmark tests we have in lattice QCD. Okay, now systematic error control, and maybe you have seen there are loads of lines here. There is the mu b over t is 2, mu b over t is 3, and mu b over t is 4 line. And I will concentrate, if you wish, most on these lines here. So as I said, we have approximations. We cannot compute all channels and all higher vertices, so we have to restrict ourselves. And what I now make is or give some insight in is the systematic error control we have for the full scattering vertex of 4 quarks, where of course also the mesons are in. So a resonant for a quark vertex, for example, in the scalar pseudoscalar channel, just carries the quantum numbers of the pion and the sigma, the scalar mode. So this, of course, you have to take into account, and that's part of the infrared dynamics we need already at chemical potential and temperature 0. So now what you can do is just the systematic evaluations. You take a Firth-complete basis, so all channels which are around, and you look which channel contributes. And what you see here is a nice result by Jens Braun and his group in Darmstadt. So what you're seeing here are all 10 channels you have. So in 2-flavor QCD, you have 10 tensor channels for Fermi interactions, and I'm only restricting myself now to the momentum independent ones. There are far more, but let's look at the momentum independent ones first. And then you look which one is important. And you see essentially there's one channel which does it all, and that's the scalar pseudoscalar channel, and the others you can switch off and do the computation again and nothing changes. Okay, and then it is at a certain chemical potential, there is essentially a flip from the scalar pseudoscalar channel to a diquark channel. And there again, you switch everything off else, except of the diquark channel, and nothing changes. So essentially you have a pattern. You have first dominance of the scalar pseudoscalar channel, and then you have dominance of the diquark channel, which you expect if you go to chemical potentials which are so high that you have color superconductivity and so on. But this means, this tells us that our approximation, which part of it is not taking account all these channels, is good for chemical potentials which are not too high. You see here the change is at mu quark over T0. T0 is the phase transition temperature at vanishing chemical potential, being 2. You go to mu b, this is 6, but keep in mind it's mu b over the critical temperature at vanishing chemical potential. So we are talking about the standard mu b over T is 7 and more. However, I mean, you should be careful with what you define as your systematic error. And if you look more closely, there's also part of the dynamics which is already switched on earlier. So we trust our approximation if it comes to these channels up to mu b over T is 4 to make a very conservative error estimate. So you can also do the same for essentially a bit differently for Dyson-Schwinger equations. Very nice works, not only one, and I mention here 2 of Christian Fischer, Gernot Eichmann and collaborators, where you look in the Dyson-Schwinger equations on the effect of mesons and baryons on the phase boundary, and you see the same in, if you wish, another shade. These effects don't play really a role up to larger densities. The other thing is what we have seen. So, okay, first of all, it tells you better make a Vierts-complete computation, and we are doing this partially, but of course, this all costs computing power. The other thing is that we see in the dispersions of what we have computed, namely the pion and the sigma field, that there is a non-trivial solution to the dispersion in spatial momentum space for larger densities. You may relate this to an inhomogeneous phase. I mean, there's a new work by Rob Pisarski and Fabian Rennecke, where they have this mode suggestion. But whatever it is, it tells us you better up your game. So that's another error bar for our computation. And this is this shaded area, this red shaded area here, and you see where it crosses the phase transition, it's about mu b over T is 4. So very conservative error estimates is please do better for mu b over T is larger than 4. And both error estimate investigations tell you we have to up our game for mu b over T is 4, but we trust our approximations for smaller mu b. And up our game does not mean we don't have results, but these are now estimates, right? These are not predictions, these are estimates. So whatever I say now concerning this regime here, let's call it as an estimate. Nevertheless, we will see that if you wish, a plot thickens, namely our estimates for the critical endpoint or point of new physics, they seem to converge, but keep in mind, estimates. Okay, as I said, we are going on there. These are now ongoing computations, so work in preparation. So we bettered the dynamics of the S core condensate, where we expected that not that much happens because that thing is rather heavy. We don't expect resonances there. And you see the old and new results are essentially on top of each other. I should take it off. Well, I happily take it off, but okay, you have to, oh, good, very good. Yeah, okay. So what we did here, this is in Dyson-Schwinger equations, we took into account the full Como electric and magnetic splittings, which we didn't do before. We had good reasons for this, not to do it, because we didn't expect it to have a huge influence, and you see it does not. Okay. So if you compute the critical endpoints in these new computations, they don't change too much. They change about 10, 20 MeV at most. So now, as you can see, that's not our computations from our group, but also the ones from Christian Fischer and collaborators. They all converge here. Okay. So since we had this discussion also, I thought about leaving this out, but I kept it in because I think it's a very, let's say, interesting and important lesson to learn. You know that there is the so-called Stefanov plot from 2004, where it was said, oh, we can't say anything about the critical endpoint. So he compiled all results which have ever been achieved by models and lattice computations at this point on the critical endpoint. And this was just plastering the whole area in the mu B and T plane. And I thought already then that this was not the best thing to do, because I knew, and I have worked on quite some of these models, and you know that some of them, and most of them, are not designed to give predictions for the critical endpoint. They have been designed for other reasons, and some of them are good for making extrapolations in mu B, and some of them are not. However, so what you should do is you just now go on and remove predictions, and I'm doing this now for the upgrade of the Stefanov plot, if you wish, which was put forward in the BESS seminar in 2020 by Xiaofeng Lu, who's actually a collaborator of mine. So again, you see, this is now 2020, you have a lot of predictions, and it looks like a disaster. But now you just go and remove things. If there's an old critical endpoint where the group who made this prediction, estimate, whatnot, has a new prediction estimate, please remove the old one. Okay, there is an improvement as time goes by, so don't cite old results. Then if you have, as I said, functional QCD computations, which are also not all of them are designed to do something at finite chemical potential, if they don't meet the lattice benchmarks at lower chemical potentials, remove them. Because in particular, if they don't meet the curvature, which is the first information you get about finite density corrections, if they don't meet the curvature, remove them. And now you see, if I do this, there's not that much left. Okay, so already, if you wish, in 2004, because you could have done the same in 2004, let's say the estimate was the critical endpoint is not close to the temperature axis. Okay, now I make a final step. If I have a model which is designed and benchmarked with the parameters at chemical potential is 0 and has a prediction for a critical endpoint which is far out, remove it. Because models cannot cover such a large distance in chemical potential. We are talking about chemical potential fluctuations, and so remove them. Okay, there's not that much left. And of course, you can say I designed it to work in my favor because I'm involved in both of these computations, but I mean, bad luck or good luck. Okay, now this was 2020. Now you go on. There is a new result from our own group, and you see what happens now is that the one result which was further out was removed. We have a revised estimate, and keep in mind, I told you this is here a region where it's an estimate, where it's not a prediction, but nevertheless, the convergence was rather good. It was not moving too much. Then there's a new result by Christian Fischer and his group, which is in the same ballpark. And I removed an old one of his, which was here, because while the curvature was not too bad, it was also not too good. Okay, and that now there's this new results with the strange Bohr condensate, it's here. So you see, because the areas which are covered here by this plot are a bit different. You see that this very dense plot I had on the the transparency before is now stretched a bit, and you see there are still differences, but as a estimate for the critical endpoint, or region of new physics, it's not too bad. Okay, so now we come to chiral dynamics, and I think this is a very hot and very interesting topic, and I had loads of discussions both with Christian and also with Maria here in the audience, and also with Fridtjof about it. So what I'm showing here is lattice results on the dependence of the critical temperature on the quark mass. And I know that Christian does not like this plot too much, how we present the results, but he will have his time to present his results himself. So, or one of your collaborators, okay? And we have now the also the functional results, both with Dyson-Schwinger equations and FRG, functional renormalization group equations. The temperatures are slightly different. So we don't see this 130 to 135. We see more 140 MeV as a phase transition temperature. However, what is actually, I think, very interesting is we can compute the full order parameter potential. Of course, in our approximation, but we can compute the full order parameter potential. And if you have a polynomial expansion in this potential, if this works, you can relate the power of the order parameter. So delta is the chiral condensate. You can also relate it to something like the scalar meson mode to the power n. Then the condensate as a function of the quark mass scales like the quark mass, of course, normalized by the strange quark mark, so some normalization to the power 1 over n minus 1. Which means that if you have a Ginzburg-Landau potential, so just if you wish a bit mean field theory, you have a delta to the 4 term, you get a scaling with 1 over 3. If you have a potential which goes like delta to the power 6, you have a scaling like 1 over 5. Keep in mind that the critical scaling you have is not 1 over 5, but 1 over 4.8 or so if you have O4 universality class. So since I've heard this many times, I have never ever said that we don't see O4 scaling. Actually, quite some of our computations press O4 scaling in, even if it would not be there. And the approximations are also made the way that they see, if at all, they see more critical scaling than there should be in, because some of our vertices or interactions are more point-like, so they are enhancing effects instead of lowering them. Okay, so now let's look at another plot. This is unpublished. So since we have the full effective potential and we can essentially compute as densely as possible, and our error bars, there's no statistical error bars. We have systematic error bars, but no statistical one. So we can really get our hand on what we call a sliding critical exponent. So we look at the local form of the scaling, and what you can see here is a plot which has two results. One is in a model, which is a so-called quark meson model, which is not QCD, but it, I mean, still, as I said, I mean, we don't have statistical error bars, but computations in QCD are just simply costly. Okay, so the dense results here in the blue is a model where we can make really make it run to a very high precision. And you see that you start at critical O4 scaling because the model is designed to have O4. Okay, so it's not the statement that QCD has O4, the model has. I'm also not saying that QCD has not O4. I think it has O4, but anyway. Good. So here we see critical scaling. And we can, in our approximation, it's very close to 0.2, right? So to 1/5, but this is critical scaling. We can also, in this RG computations, you can just look at the Witham scaling form of the full potential, so we see it. So we have subleading scaling, what you wish, we have it. Okay, and then we are deviating from this rather quickly. We jump up, if you wish, to something that's very close to Ginzburg-Landau. So you can say that the critical scaling region is surrounded by one where you have something like mean field scaling, right? And then it comes down again, which does not mean you're coming down to critical scaling, it just comes down, right? And then there you see that you're crossing essentially, again, the critical O4 scaling regime, very close to, if you wish, physical quark masses, but that is what we have. Keep in mind, this is the model, and the models usually have the property that things happen far quicker. And what you see here, the red results are actually QCD results. So the shape is the same. The errors are, of course, bigger because it's, I mean, numerical effort. So that's what we have. Okay, so you see, I mean, I made these two things. You have critical scaling here, and of course, I mean, in approximation, it may not just show if you have 0.4, this 4.8 something, but I mean, it's there. And then you have trivial, if you wish, delta to the power 6 scaling. You have trivial delta to the power 4 scaling. Okay, and we see this all, and we see also how it deviates from the critical scaling. And look at these masses. They're very small. Okay, now you can take this and you can make a plot, which we did. Actually, and what we have here is the critical scaling as we see it. It's a very small regime, and it's surrounded by a regime where you have essentially delta to the 6 scaling. The important thing is here that you don't have a mass term. If you would have a mass term, you wouldn't see the scaling, okay? And then you have a large regime where essentially the whole thing is governed by Ginzburg-Landau. And then if you wish, there's a regime where nothing, it's boring, okay? So you have a quadratic term which tells you, yes, you have a channel. That's it. Okay, and you can also see, I mean, we put this in here, that's the physical point. Right, and of course, this region, very interestingly, about the critical point, so the critical limit goes far more out to the mass plane. It's not critical scaling, but I think what is interesting and very important for Phino applications, it is quasi-massless. And that's the thing you need. If you want to do chiral transport, what you need is not criticality. You need quasi-massless modes. And that can be ensured in this region. We are working at the moment on getting this plot also for finite chemical potential. What we also can provide actually is the order parameter potential, which actually would be interesting for transport codes. You can put it in there. You have an effective potential, which also includes quantum chemical potential. And okay, now it's frozen. Good. I think it's the computer which is frozen here. So my apologies to the audience here. It's going on, I think, on the slides, right? No, it's frozen. Ah, the connection is gone.
So we are sorry, we have some technical problems, but we are solving that now.
I think I'm thrown out, so I will start it again. So I'm wasting my time on this. No, this was a joke. Okay. Okay, so it should be back. Okay, so now I'm leaving QCD and I'm going to effective theories. And I would like to convince you that, of course, there are applications where this really is a good thing to do. So, and I call this on the unreasonable effectiveness of low energy effective theories. And I mean, those who are children of the 80s certainly recognize the title. So what I want to say here is that there's sequential decoupling of fluctuations. And what I'm showing here are the couplings. Here it's the quark-Gluon coupling, and it's an exchange coupling. It's the coupling you have in these diagrams here, which is a contribution to the flow or the dynamics of the quark 4-point scattering kernel. Okay. And now the first diagram we have, keep in mind in the flow equation, everything is one loop, is this object here, which looks like a perturbative diagram, but it's not. It's a full gluon propagator, it's a full quark correlation function, and it's a full quark gluon vertex. So it's a complicated beast, has a lot of channels. Now, if you look at the coupling strength of this object, obviously, if you go to large scales like 10 GeV or so on, it's the only thing around, right? It's a gluon interaction. And for quite a while, this dynamics or enhancement of the dynamics is driven by the strong coupling getting stronger. That's what you see here. Okay. Then there is another coupling, which is already, if you wish, sixth order in the quarks. You have, because we have channel interactions, so there's the scalar pseudoscalar interaction channel, which in our case we call the pion and the sigma. It's a bit a misnomer because it's just a channel field. We take this into account, and of course in the perturbative regime this is totally irrelevant. Keep in mind this is a doubly logarithmic plot, right? And it stays irrelevant for quite a long time before it takes over. Okay, and it takes over from the original gluonic interactions, and they switch off very rapidly. The gluonic interactions go to zero, and that comes from the fact that we have a mass gap in QCD, and that is reflected here in this interaction couplings going to zero. Okay, and then, I mean, if you're at these scales here, but keep in mind, this is already 200, 100, 200 MeV or 300 MeV. The gluons are gone. They are not driving the dynamics anymore. They are a background, you need them for that, but they are not driving the dynamics anymore. And we are talking about off-shell dynamics here. So you have to always keep into account there's a difference between on-shell or asymptotic states and off-shell, which you have in diagrams, or in on the lattice, it would be the difference between C and valence quarks, for example, okay? And then, of course, so then you have the pions and the sigma. The sigma also decouples then rather quickly because it has a large mass of about 400 to 600 MeV. And at some point, of course, also the pion decouples because we have a physical pion of 100 MeV. So what you're seeing here is that from these four diagrams, they decouple more and more. Okay, so you have the gluons, they decouple first. The ghost, because we have a gauge fixed approach, is of course still there. It's massless, but it communicates with all the other fields only via the gluon. So if the gluon is decoupled, the ghost is gone. Okay, and then you have just your meta sector, which means you have, if you wish, a first principle derivation of low energy effective theories here. You can go to chiral perturbation theory, can derive chiral perturbation theory within this approach. If you think that you want to keep some other, let's say, modes around, they will of course show up. And it gives you also maps between these different low energy effective theories. So they are no different in our approach. They just come from the same thing, from QCD dynamics, and the rest of the dynamics then decouples. Which means that if you tune the coupling parameters of these models, I mean, they must be sufficiently complicated. You cannot now just do mean field. You have to really take the relevant dynamics around alive. So, but if you tune the coupling parameters of these models to the ones of QCD, you're talking about QCD, right? And one of the things is that now if you go to the phase diagram, and then, of course, if you still want to connect these models to QCD, you have to retune your classical parameters in these models, because the QCD parameters, which go into the classical couplings of these models, will be temperature and chemical potential dependent. If you don't do this, and of course, in most model computations you don't, you lose gradually contact to QCD. That's why I said, don't trust model computations which tell you the critical endpoint is at 700 MeV chemical potential. Okay, so we did this for looking at fluctuations in conserved charges. We are now also doing this with the full QCD code around, but these are our results. Again, we call this now QCD assisted low energy effective theories because our parameters are set from QCD. We look again at our benchmark tests at zero chemical potential. We look at fluctuations from the lattice, and we have quantitative agreement with these results. But keep in mind, if you go to the higher moments, quantitative agreements means less and less because the lattice error is increasing. So, I mean, the better the lattice results gets, the better also this benchmarks will get. And now we can look at finite chemical potential. I will only flash through the results. As Jana also said, for the Wuppertal Budapest results and also Claudia, they sort of fit to star data, but keep in mind, I mean, these, we are talking about non-equilibrium processes. Maybe it's not too good that the things fit too early, but I mean, that's what they do. Okay, so again, I think this is a great opportunity for combined analysis. And if you wish, we have to work or walk our way through from small chemical potentials to large chemical potentials, and giving the combined limitations of all the approaches we have, we need all, in my opinion. Okay, last thing, we have already heard about the Taylor expansion. Keep in mind, now I'm talking about model results. Nevertheless, what you can see here is a comparison of our QCD assisted low energy effective theory fluctuations with Taylor expansion. And we did Taylor expansion taking results from the lattice, and we did Taylor expansion with our results. Of course, this more or less agrees because our fluctuations of conserved charges agree at vanishing chemical potential. And now what you see is that what we see if in the full computation without Taylor expansion, that some wiggling is starting. And this wiggling is physics, because you go back to this plot here, which is the freeze out curve in the model now. And what we plot here is a contour plot of the kurtosis. So where it's red, it's positive, where it's blue, it's negative. Now, what you usually do is you keep your temperature fixed and you increase chemical potential. Now you can already see that if you're going through the phase structure, for example, at 150 MeV, you take a horizontal line, you will go from positive to negative and back, and which means it will fluctuate. Okay, and that's what we see here. So this fluctuation here, that's not Taylor expansion, that's the full result. Okay, while the Taylor expansion shows you a nice monotonic behavior, but it starts deviating from the full result at some point. It cannot capture this, right? Okay, and it will not capture this. And why should it? I mean, we know that at 3, I mean, mu b over t is 3 or 3.5. We know that we have reached the convergence radius, right? So whatever we do, we need more. And I'm just saying that, I mean, as I said, if we have a truncation to functional QCD, which fits all these benchmarks, which are now getting better and better, I'm really impressed by the progress which has been done on the lattice. So now we are talking about going up to mu b over t is 3, then we can go on. And what I insist on, functional QCD gives you the best extrapolation of QCD data from low chemical potential. If you disagree, tell me a better one. Okay, so we are also doing non-equilibrium processes, but I knew the time would be up. So I will stop here. I'm sorry, Maria, we can discuss this I think in private. It is very interesting because with all the constraints we have on different directions in the phase structure, also many flavor. I mean, that's one of the things I really like. Also here, I would like to say, I mean, I think it's time for a combined study because we all have to. Yes. Okay, and the talk, I think, will be also on the net. So,
okay, thank you very much, Jan. So I'm pretty sure we can come to this in some discussion session, and that's really interesting features and very important. But now let's come with the questions to this particular talk. Okay, Jörg, just a second, I have to give you a microphone.
I have a very trivial question, which I missed probably, but how you determine the critical line? I mean, on the work-fluent sector, you have very nicely shown what you are doing, but how is about the hadronic sector? I mean, for a phase transition or for a critical line, you have to have both.
So this is why I said we are looking here at the chiral critical line, and we determine in, as is done on the lattice, we take a chiral condensate and we're looking at susceptibilities. What I'm showing here is the thermal susceptibility, but we're also looking at the magnetic susceptibility. So this is our definition for the crossover temperature. And of course, depending on the observable you take, they vary. But of course, the critical endpoint is unique.
Yes, and then when you go over the critical endpoints, then you get more in troubles because then you have really to take the hadronic side.
Then you have, so we have results there, but they are so, we have them since quite a while, but we didn't concentrate of them. I mean, we can go on.
I wonder, because you have your critical endpoint, which you have here, is about 600 MeV. Now we know that for T equals 0, we should come something like the baryon mass for 3 times the quark chemical potential.
Yeah.
So it seems to be that this extrapolation is not a very smooth one. I mean, if I take your curve and continue to T equals 0, it ends up something like 700, 750.
Christian Fischer has done this. I mean, there's a nice plot and discussion in his review from 2019, where you can see if you extrapolate this curve, it's suspiciously close to actually also liquid gas transition. So of course there are speculations around, as you know, that I mean this ends in the. I'm not taking any side here, okay? Yeah. Yes, so what we are doing at the moment is we are also taking the diquark channels into account. Keep in mind, we are talking about off-shell fluctuations, and that's not the baryons, it's the diquarks which really run the show. We have tested this 5 years ago, actually. Sorry? No, we have. I mean, we have now approximations where the diquark is a dynamical degree of freedom. So if you wish, the best approximation we are working at the moment on has the diquark also and has the density mode. What we have seen already, if you take the diquark, I mean, we tested this in the model, the phase structure is, if we have the density mode, the phase structure is not changing. But if you look at something like in this language of a Waleczka model, essentially there's an effective chemical potential. And if you let this agree with the chemical potential, you see this essentially the same. I mean, it's really quantitatively also the same. With the diquark, it's a bit more complicated, but I mean, so stay tuned, yeah.
Okay. I see some question from Fritjof. Fritjof, please.
Yeah, Jan, hello.
Hi.
I have a question to your slide where you show this critical region. You had a parameter.
Do you know roughly the number?
No, sorry. Where you had the phase diagram, we see small region around TC, and where you give.
The
Yeah.
next one you excluded some. Yeah.
Yeah. So I was actually wondering about the equation you give there. So how should I reconcile this with our standard thinking about randomization group behavior and critical behavior? How would I would, at least in the standard picture, we talk about a phase transition in, let's say, the O4 universality class, plus regular terms in the contributing to the order parameter.
I have left, Fritjof, I have left a lot out here.
That's why I just try to understand how do I get these other fractional exponents in the language of renormalization group? You have other fixed points there or what?
No, we have the full potential. You can make a fit to the full potential, which has, of course, the subleading scaling, and then you get the subleading scaling coefficients as well as the prefactors out of this. I mean, that's actually something which has been done back in 2010 by Jens Braun and collaborators already.
But do you claim that there are critical exponents which lead to 1 over, it's of course not the 1 over delta, but you get a 1 over 5 and 1 over 3?
No. Wait a second. So this parameterization, thanks for the question, this parameterization works away from criticality, okay? So this parameterization works in a region where the critical part is not present effectively, okay? And of course, if you now come close to the critical region, this parameterization which we have, there's a delay here, okay? This parameterization which we have here is not working. Okay, so we have done both. We have made a parameterization, including the critical scaling and the subcritical scaling, and we have made this just simply for the reason that this works well in a huge regime of this phase structure. And that's something which, of course, at the very end, if you do something like chiral transport, you would use. So
well,
I'm not.
Yeah, okay.
Yeah.
I find it's very strange. It's not our standard language about critical behavior plus regular terms. So this is not a regular term. This, for instance, would say that when you take out the O4 part, you still see a diverging susceptibility with an exponent of 1 over 5 minus 1.
No, Fritjof, I'm not saying that this works close to the, I mean, this works at this red point. Keep in mind, I mean, the critical region, you can say, at least in our model or in our approximation to QCD, is abysmally small. Look at the plot. I mean, we are talking about, I sorted, I mean, oops, man, something is. So this area you have on the left-hand side of this plot is the one where you have critical scaling. And we are talking about pion masses of 0.01 MeV. Let's be generous and go to 10 MeV pion mass to cover everything, whichever can be covered by this critical plus subcritical scaling. Then we are still far away from anything which we are interested in. That's the statement here.
Well, I would be more interested to know whether this term exists in QCD. So I guess you are small scaling region or not. Question is whether the rest is just a regular term, so you need higher powers in H, or whether you have some critical exponents there. So this is sort of not in QCD, I would say.
No, this is in QCD. And this is the parameterization which works far away from the critical region. And there it's pitch perfect. I'm sorry. Okay. And you can question that this is QCD. That's fair enough. Keep in mind, this is an approach, which is an RG approach. And we have tuned it the way that we see criticality, even if it's not there, if you wish. So if it does anything, it enlarges the critical region. We know how to spell subleading corrections, Fritjof. So if you wait, let's say half a year, we will also have this analysis, including getting our hands on the critical region in QCD with the scaling term and the subleading scaling term.
I'm sorry, I have to interrupt your discussion. We are out of time already. So very short question and short answer, please.
So this 1/5 scaling, for example. So I mean, in the relation between the exponent delta and the dimensions of you know, in this relation, if I put d equal to 3 and eta, the anomalous dimension 0, I will get 5, right?
I didn't understand the question.
So, so the relation between the exponent delta and that is relation with the dimension plus 2 minus anomalous dimension something that relation gives me a delta equal to 5 if I put d equal to 3, right, with eta 0, and that eta being non-zero in dimension 3 gives me the O4 exponent delta.
I make
right?
a different statement here. Okay, this is an expansion which reflects. So this is why I made this comment here: non-critical scaling. Okay, this is an expansion which is one-to-one to a polynomial expansion of the potential, which you can do if you are far away from the critical point. If you go close to the critical point, everything you're saying is correct. Then if you remove the eta, you get 1/5, right? And so on and so on. You get subleading terms. Then this is an approximation. This all works. What you are saying and also what Fritjof was referring to works. Wow, shit. Okay, works in this small regime, which was covered in red. Okay, which had quark masses which were far less than 1 MeV. There, everything we know about criticality works perfectly. And you can check it. And actually, in the functional renormalization group, this has been checked more than 10 years ago by Jens Braun and Bertram Klein.
Okay, I think we should thank Jan a lot, and you can use the possibilities that you are in presence and have a nice discussion during coffee break or dinner or whatever. So, and thanks to Jan.